All right, good afternoon, everyone. My name is Nicholas Morgan. I am the program coordinator for the Aim for Composites program, and I'd like to introduce you to our summer research internship program of 2026, uh, presented by both Aim for Composites and Ideas Collaborative Research Trainingship. And this is our one of three webinars that we will be presenting for the summer. So, Aim for Composites is a program that its mission is to build an AI-enabled inverse design approach for fundamental understanding integrated material manufacturing design for advanced polymer composites. And the Ideas NRT trainingship focuses on training the next generation of STEM students to develop expertise across multiple disciplines, specializing in AI-enabled inverse design, advanced composites, and sustainable manufacturing. So this webinar series starts talking about the role of neural networks, which is the stepping off point for artificial intelligence. And this webinar series will be presented by Hanzo Wen, he is a grad student at Clemson University, who is volunteered to present this material. And just a quick acknowledgement to our to Aim for Composites and the ideas and ideas NRT. Um, and just so for your knowledge, our next lecture two, which will be more of a hands-on approach, will be on June 29th. So I will be sending out an invite uh, and this week. So just keep your eyes out for that. And without further ado, I'd like to turn over to Hanzo so he can go ahead and get present.
Yeah, thanks, Nick. So today we are like driving into exciting world of AI. So the first topic today is aim to introduce the fundamental concept of the machine learning, and especially focusing on its versatility in manufacturing, material design, and thermal engineering. And another topic is about the biomedicine. So this is our first webinar of the summer research program. So there are just not like what Nick said, there are two more hands-on tutorial webinars in the later time. In the later two webinars, we're going to learn how to use and program machine learning codes in Python. Today, we're just focused on the introduction part and to show you the multiple scenarios of scientific research and engineering process that we can apply in neural network-based machine learning. So to start, let's define AI. So AI, artificial intelligence, usually refers to the simulation of a human intelligence in machine programmed to think and learn like humans. AI has evolved significantly since its inceptions, with applications range from simple automations to complex problem-solving tasks divided by the stages of in the evolution process. So we can generally divide the several different types of AI. So the first stage is a narrow AI, which performs a very specific task. So it can match or even outperform human in that specific task. Many mature AI models and or algorithms have been already applied in area like media recommendations, face recognition, self-driving modern car industry. Then we will have general AI, which can ideally perform any intellectual task as human can. So the general AI will have a ability to understand, to learn, to apply knowledge across a wide range of tasks, just like human. Current large language model or LLM-based generative AI tools like ChatGPT, its underlying reasoning and thinking model can be considered as the early models of general AI. And just in the recent couple of months, there has been a very popular and hot tool is what we call the agentic AI. So unlike the traditional AI, which waits for step-by-step instructions, the agentic AI can set goals, create its own action plans, and use tools to execute complex tasks by minimal human supervision. So this means we have created AI that can process complex tasks like highly skilled human beings. For example, in the coding area, there are many agentic vibe coding tools like Cloud Code Codex from OpenAI, Gemini from the Google, which can automatically produce perfect coding files for every complex project. So we're already on the way to a real general AI. Then what's next? Maybe ultimately we will have Superman AI, which is supposed to, surpass human intelligence in every field, including creativity, decision making, and emotional intelligence. It will be smarter than the best human minds in every way. But those already exist in the sci-fi movies, like for example, like Jarvis in the Iron Man movie or Skynet in the Terminator movie. So under the big picture of AI, machine learning is among many specific areas. Data-driven is a core concept of the machine learning. So it means that we teach computers to learn from data instead of programming every rule manually. We let the system learn the patterns and makes predictions. So a simple example is that if we want to design a module in a thermal system to determine the thermal status, in traditional programming, we would explicitly state the rule to the machines, where the machine just follows the rules that we define. In machine learning, we don't define that. We just give a data set to machine, and the machine learns the pattern of the temperature and the thermal status. Even eventually predict what the thermal status will be if the temperature value is not inside the original data set. So under the framework of the machine learning, deep learning is one of the most popular ways that is commonly chosen for a machine learning task. The model of the deep learning lies on framework of the neural networks, and the concept is inspired by the human brain. So the ADJ deep refers to the use of the multiple layers of neurons inside of the whole network. The whole process is that the raw data comes as the input port, and through a series of mask operator inside the neural network, the target outputs comes out. So if we use the previous example of the determine how thermal status according to the temperature, so the input is the temperature and the output is the status of the hot or the cold. So one amazing thing about the deep learning that it can automatically extract the future from the raw data. Thus, we don't need to do anything manual. So if you consider the whole networks as a black box, the only thing that we need to do is to set up the input and the output. But how does the neural networks or NN has the ability to learn pattern inside the data? Or to say, how does NN find the relationship between the input and the output? In the pure perspective of the math, the input and output data is nothing but a series of a group number. What we want is to find the mapping or function between the input and output. So the universal approximation theory basically tells us, so for any continuous function, there will be a small f of x and any error tolerance larger than 0. So there will exist a neural network which can refer as a big f of x with at least one hidden layers, such that the gap of the two f of x within the large of a small error, that there gonna be always be an n representing a big f of x to approximate the function of the small f of this. So the concept is pretty similar to the math series that we learned in the fundamental math class. So we know that if given with a continuous function like f of x, we can use Taylor series or Fourier series of multiple base function terms to approximate it. And by using more terms and adjusting the right coefficient AN in each term, the approximation result will be closer to the target function. So the idea is to use an approximator consisting of a series to approximate the target f of x. So the NN is based on the same idea. So for NN, math series are replaced with the structure of neural networks. So the base function terms are replaced by the neuron inside the NN, and the adjustable coefficient AN are also replaced by the weight and biases in each neuron. The evaluation of the approximation quality is represented by the loss function, which is defined as the gap between the prediction and target functions. And what we want is the loss function as minimal as possible. So the NN is doing the same thing, which is to approximate the target function. So the lower loss that we have, the better approximation we will get. Not only limited in the range of the mass functions, NN's approximation ability can be used for more complex and abstract scenario. So a classic example would be the image identifications, where we can insert the images of the animals as the input, and let NN to determine which one is dog or which one is cat. So complex problem like image classifications, neural language processing, speech recognition, auto drive, forecasting on a complex time series can be sufficiently solved by NN-based models. The reason that NN has a strong generation power for different and complex scenarios is because NN has a highly adjustable complexity. NN can be really complicated with the thousands of billions, even trillions of neurons. So this basically allows NN to have ability to deal with a super large amount of data. However, the advantage of the NN sometimes can be a disadvantage, because collecting and organizing a big data set for training is not easy. And training NN involves massive data, and neurons usually consume a lot of computational power. So people start to use more efficient hardwares like GPU or TPU to do the NN training. So how to reduce training costs and use a smaller NN model to train large data set is one of the ongoing and important direction that people are working on. And our main topic today is scientific machine learning. That's why let's take a step back and think about how humans solve scientific and engineering problems in traditional ways. So for centuries, we've relied on the power of fundamental physics. So these physics laws like Newton laws of motion or Navier-Stokes equations are beautifully compact and mathematical description that governs everything from folding apples to turbulence flow. Those laws enabled us to design bridges, design like rocket, smartphones, or any modern designs that we know. So the extension of the boundary of the fundamental physics and the inventions of a new design are really come from the decades of the research. So conventionally, there are two ways. One is to conducting the actual experiment, and the other is run numerical simulation on computers. So these are methods are very powerful, but they can also be expensive, time consuming, or limited by the computational resources. But now we have a third approach, which is to develop a surrogate models using neural networks. So these models don't replace physics. Instead, they learn from the data, either from the experimental or simulation approach. And they offer a faster way to approximate physical behavior or engineering process. So surrounding the scientific machine learning, so we can use NN to explore the hidden physics to push the boundary of science. We can also use NN to solve engineering problems in a more efficient way. We can also use NN to assist our modern engineering design. In the following content, so I'm gonna introduce 4 specific topics to elaborate how to use different neural networks models to solve a variety of engineering and scientific problems, and hopefully give you some insights in how to incorporate NN into your own research and engineering design. So let's first talk about the composite materials. So things like carbon fiber, fiberglass, or reinforced polymers. Over the past few decades, scientists and engineers has been designing new structural composite materials to meet the growth demands of the modern technology. Researchers began combining materials, taking the best property from different components to create the composites that are stronger, lighter, and more flexible. So for example, in aerospace or automotive industry, using a composite instead of conventional metals can dramatically reduce weights, improve the fuel efficiencies, and eventually enhance the safety. So when people came up with a new design of a material, the first thing they need to do is to test the mechanical performance of this new material to say whether the mechanical properties of the new material can reach their expectancy. One of the common employed and cheap ways to conduct element analysis by giving different levels and patterns of loads in the simulations. So designer can pre-examine the deformation pattern of their new design material. Thus, validate that in this way to validate their design's reliability and eventually improve the design. Even though compared to the actual experiment, FEM simulation would save a lot of time or money. But sometimes a lot of simulation, especially the ones involved with the complex geometry, multiple material components, usually take a lot of time to finish. So our motivation here is to whether we can develop surrogate models to replace this process. If we have a well trained neural networks, whenever there's a new similar material, we can just insert the material into our NM model, and instantly we will get the test result. If we try to use a simple math language to describe this FEM process, so there will be a load function that we gave to the material, and the simulation would produce the response function. So our mission is to develop a surrogate NM to approximate the mapping between the load function and the response function. So in regional math, we refer a mapping after one function to another function as an operator. The simple example is the basic differential and integration that we learn in the math. If we do the first differentiation on x squared, we'll get an outcome of 2x. So both the input and the output are in the form of a specific function. So back to our NM, just we learned before, the universal approximation theory ensures there's always an NM that can approximate the mapping f from x to y. So we extend the x and y to the function a and b. Theoretically, we can build an NM-based operator to map function A to function B. Therefore, we can build a deep neural operator, or DNO, to approximate the mapping from the dynamic loading function to a mechanical response function. The structure of DON is composite of two major parts. One is branch net that takes the node value as the input, and the other one is a trunk net that takes unchanged times sequence as output. If you consider a dynamic strain node, the load function, it has a strain on the y-axis and the time on the x-axis. For different node patterns, the strain value on the y-tick is changing while the time tick on the x value is unchanged. By multiplying the two matrix products from two nets, we will get the outcome sequence, which is a mechanical response sequence. So after knowing this model, here is the process of the problem setup. Since the NN is data-driven, we're going to need a lot of data of load functions and the corresponding function to train our NN. Therefore, FEM simulation is conducted to provide enough data and also provide a reference comparison. Those data are fed to NN model. Once the model is well trained, you should predict a response function given random dynamic node function. So we built a beam with a composite, steels, and aluminum material. We gave dynamic strain of load function at the free ending of the beam as the input of the simulation, and therefore a response temporal force function as a fixed ending, and the normal distribution along the x direction as the output in this simulation. After the simulation, those input and output data is given to our DNO model to train. So this is a dynamic force prediction result that given by DNO model after the model is well trained. So the average accuracy is around 98%. There is only one local misalignment. So the overall prediction is very accurate, and this proves our DNO model is pretty reliable. So the stress predictions also look pretty good in both compression and tension, and uh, the average predict accuracy of the model is also around 98%. So the relatively large error could be a reason of plastic hardening since we introduced the dynamic loading, and the plastic mechanics is nonlinear and it's hard to learn by the DNO model that we use here. So the test to find the relationship between the model's performance and the size of the training data is also essential in training a surrogate NM model. So in our DNA model, in case there's beam mechanics, the dataset with size of 2,000 to 3,000 is the best choice, which offers decent accuracy with a mid-sized data. So whenever you design your NN models for those scientific or engineering problems, so this step is always considered as parallel because it helps you to determine what size of training data you should use to give the model the highest accuracy with relatively lowest cost. DNO model is also faster to train than the conventional deep neural model. And if the codes are implemented in the JAX, the training speed is even faster. Another key element you may consider as a priority is to test the optimal NN structure for the model, and the higher complexity of the NN structure doesn't always guarantee a higher accuracy. So every time when we build and test NN, we need to find the optimal architecture. So in this case of the DNO model, 3 hidden layers, and each layer consists of the 200 neurons of the optimal structure here. So robustness of the neural network model could be also critical if the training data is obtained from the experimental data with inevitable noise. So the error generated due to the inserted noise is less than the percentage of the noise. That shows the DNA model demonstrates the robustness in this task. So the test of the robustness is also necessary because in the real world engineering process, there are always going to be noises that introduce error in the data set that you collected through training your AI models. So the higher the robustness or the fidelity enable your NN model more convincing. Sometimes if you found your NN model's performance gets significantly worse than with a small noise, it means you need import modifications or changes on your model to make it more robustness. So our DNO model is fast, robust, and accurate. Through the first topic, we are learning the structure. The DON is suitable when approximating the mapping between the function to functions. In your research or design for an engineering process, if you found two important functions that share correspondence, this might indicate you to try with our DNO structure. So for our second topic lies on the utilizations of biomass. The biomass is a key player in the development of a sustainable energy and material. Amongst various types of biomass, coal stands out as one of the most widely cultivated crops in the world. So beyond its role in the food production, coal and its byproducts are also a valuable feedstock for producing bioenergy or bioproducts. This makes it an important resources in renewable solutions. But before the biomass can be transformed into useful fumes or chemicals, it needs to go through several pre-processing steps. And one of the most critical steps is size reduction. So why it is so important? Because the raw biomass, like the core stock, is bulky and difficult to process directly. So reducing its size can improve handling, increase the surface area, and enhance the efficiency of a certain downstream process like chemical conversion, fertilizations, and combustions. So in short, the size reduction in biomass pre-processing is very important for converting raw agricultural residues into clean energy and a valuable product. So we cooperate with the Ideal National Lab to study the biomass size reduction process. From them, we have known that the size reduction process can sometimes causing jamming or equipment shutdown. So we're thinking that if we can understand and predict the size reduction process well, so in this case, we can prevent the plugging and improve the efficiency of the biofuel production. So here it shows the main components of the milling machines. So it has a hopper and the mill through for the raw biomass to go through, and a mill chamber to cut the biomass. The screen is placed at the top of the mill chamber to control the output milling size. The grilled biomass finally will drop into the collection bin below. So for many years, the successful proceeding of the milling process highly depends on the experienced workers. Those workers has been operating this machine for like more than 20 years, and they know how to change the machine parameters when the machine is jammed or plugged. So we work with Ideal National Lab to see whether we can use machine learning to help improve the milling process. Just like we did before, we want to simplify the milling process into a basic math language, which may give us a hint about how to design our NN model. The key process of milling is to reduce the particle size of the corn biomass. We can use a cumulative distribution function. Is to describe the size distribution before milling and after the milling. So before milling, the raw biomass have larger particle size. So the distribution is in large range of the 10 millimeters to 30 millimeters. While after the milling, the particle size or the safe size gets smaller. Thus, the distribution of the size is smaller than the 5 millimeters. So we still use the previous mindset. So we will find the milling process essentially the mathematical mapping from the from feed raw biomass cumulative distribution function to output biomass cumulative distribution function through a milling machine. Therefore, we can still use the framework of our DNO model. So different from our previous composite bin case. So the milling process of biomass is actually involved with some external parameters. So the experiment worker would automatically know what would the raw product look like by knowing which screen size the milling machine is using and how moist the raw biomaterial is. So we need to modify. So for that reason, we need to modify our DNO model to upgrade version. So to do that, so we incorporate the influence of those parameters. Thus, we added an additional parameter net to inform the neural network with parameters information. Here we can see the predicted cumulative mass distribution of the corn biomass from the DNO plus model. So this prediction aligns well with the reference data, achieving about 99% accuracy. This means the model does a very good job of capturing the overall trend of how biomass accumulated across different particle sizes. So this high level of agreement shows our DNO plus model. DNO plus model is not only fast, but also reliable for approximating the biomass size reduction process. However, in reality, collecting biomass data to train a surrogate model can be sometimes very time consuming. So even after several years, the amount of the high quality and usable data that we have in our hand is still less than 100 samples. So to address this kind of the limitation, we looked into developing a model that could work with less data, and that led us to explore the physical informed DNO plus models or PI DNO plus. So in this way, we can use a population balance model, which is a simulation model to expand the size of usable data set. So that's reducing the need for large amount of data from the actual milling experiment. Here we can say the predicted cumulative mass distribution of the core biomass using the updated model. Compared to the pure previous DNO model, the accuracy is slightly lower, about like 79%, but still very strong. So the prediction continues to align well with the reference data, meaning the model still captures the overall trend of the biomass and accumulates across different particle sizes. So even with a fewer data points from the actual experiments, thanks to the data interpretation of the PPM, the model remains reliable and the efficiency in approximating the size reduction process. The previous model includes an additional parameter network, which allows the model itself to incorporate the influence of the important external factors, and it performs very well under those conditions. We also couple the DNO plus models with the PBN simulation as well. So this helps reduce the network's reliance on a large amount of training data, making it much more efficient and practical for the real world applications. So these results highlight the very strong generalizability of our DNN framework, which is flexible and adaptive. So for the third topic today, let's begin with the governing equations, which are the heart of the most physical models. So these equations are usually written in the form of PDEs, and they describe the fundamental physical laws, things like conservation of mass, conservation of momentum, and conservation of energies. So PDEs are incredibly important because they help us model a huge range of the real-world phenomena, from the fluid flow and heat transfer to wave propagations and so on. Usually, solving these equations exactly is often impossible, especially in a very complex system. So that's where the numerical models come in. Numerical models for PTEs form that from the fundamental of the modern computational simulations, whether you are designing a race car, thermal radiation system, or aircraft, you are likely solving the PTE under this rule. So when we talk about the classic PTE-based numerical simulation, there is a conventional mindset or layout to follow. So the first step is to clearly define the physical problem using the appropriate governing equations, usually in the form of PDEs. So these equations capture the fundamental physical laws involving inside the system, like fluid flow, heat conduction, or wave motion. Then we are going to build the actual geometry of the system and apply the necessary boundary condition and parameters. This means setting up things like domain size, walls, inlets, outlets, physical constraint, material property, and so on. And the final step is solve the PDE numerically. So using methods like Feynman difference Feynman element method or Feynman volume methods. The result is like a numerical solution that approximate how the system behaves over space and time. So the softwares like COMSOL, ANSYS, APAS, OpenFOAM are favorable by the engineers and the researchers. If you are good at coding, you can write your own software. The mindset has driven decades of the progress in simulations and is still the backbone of the most computational physics tools today. But as problem gets more complex, the data becomes more available. Researchers have started looking for new ways to complement or even rethink this traditional pipeline. So that's where the machine learning comes in. At first, it was used to assess the simulations. One example is to refine the resultant physical field resolution. That is a simulation run relative low resolution, and the machine learning interprets the result into a higher resolution one, thereby reduce the computational effort. Another one is to use machine learning to automatically generate or optimize the merge that we're going to use in the numerical simulations. But in recent years, we have seen a growing trend where machine learning is used to solve the PDE directly. And that brings us today's main focus, the physical informed neural networks, or the PINN. So PINNs blend with a structure of the physical laws with the flexibility of deep learning, offering a new approach to solving forward and inverse problems, often with less data and no discriminations at all. So let's look a closer look what makes PIN so special. So just like I mentioned, the essence of the governing equation-based simulation is to solve the PDE by numerical means. So if we assume there's a PDE in a simple form, so our mission is to find the solution in form of f of x, y, and t. So if you already think about the mass essence of the solution f, it is a mapping that turns x and y t into a result u. Remember what we talked about before? We can use a surrogate NN to approximate this mapping based on the universal approximation theory. And by minimizing the gap between the NN's prediction and the real solution, we would get a approximate NN solution. But what makes PINN so special is that the model introduced the additional physical information from the equation itself as a physical constraint to regulate the approximating. So to say we are in the process of training where the blue NN mapping is not good enough, but is still evolving. So in every involving step, we can extract the local partial derivatives through arithmetic differentiation. So those derivatives should obey the PDE itself to say in the math, the operation result of the three of these sum of those derivatives should be zero. So therefore, we can define an extra loss to quantify how well the NN's derivative satisfies the governing PDE. Therefore, a physical constraint is imposed to the NN. So the mission should be to minimize the total loss from the original definitions and also from the PDE as well. So another important thing to notice that when optimization try to minimize the original loss, we need to know the exact value or the reference value in the field. Since the NN mission is to find these values in the field, only periodic and login values that we can use for is are the specific boundary conditions of an issue condition. So the training data in minimizing the original blue loss here is sampled from the boundary conditions or initial conditions. Meanwhile, if you think the definition of the physical loss, we don't actually need any knowing field of the value as reference. So the training data for the red physical loss can be sampled from anywhere within the whole domain. So this is a very important thing to notice in using PINN. We need to know where to sample the training data. So basically, PINN is approximating the solution of the PDE in both directions. So the first is predict solution should look like the real solution. The second one is the predict solution should satisfy the governing PDE. So here we use a very simple case of a heat transfer problem to demonstrate how do we use a PIN in solving PDE. So here we consider a 2D square domain without any heat source of sink inside. The governing PDE will be a very simple Laplace equation in a steady case, or Poisson equation in a transient case. We consider the material inside the domain has constant thermal property, and the value of the property is self-defined. So the PDE would look in a very simple form. For comparison, we use composite to generate a reference solution of the three steady cases and one transient case. And the three steady cases on the right side are given different boundary conditions at the right edge of the domain. Then the transient case on the left side are simulating the temperature field from the time 0 to time 1. So this is a solution result predicted by PNN compared to the console result. So you can say two results are really close, and the overall accuracy of PNN is around 98% to 99%. So the only mismatch in this is in the marginal area of the domain, specifically in the four corner of the square, which is understandable since the large gradient would generate in alternate area of the two boundary conditions. So this means the console may give inaccurate solution in those areas as well, but the overall prediction is very good. So the rest one is the steady case where, and the transient also show the same level of the accuracy as well. So this means the PNN can solve a PDE just like a conventional way, where we know the PDE form and the only boundary conditions and trying to get the solution. So those results are showing the compatibility of the forward PNN, but PNN can also have something very unique, which is the inverse discovery. Let's try to imagine a scenario where that we invent some new material and we wanted to find out what's thermal properties of the new material. So the challenge really lies in that we may not know which term should appear in the thermal equations. So it will be hard. It will be hard to directly determine the thermal property of the material. So the mission of the inverse PNN is trying to help us to fix this problem. Since we use optimization to determine the weight and biases in the neural networks, we can also put determine the thermal coefficient in the PDE in the training process as well. So we let the NN basically tell us what kind of coefficients are optimal ones to match with the PDE. So this result shows that two scenarios. So scenario one is that we have the physical intuition to say we know what kind of a physical form looks like, and we just don't know the exact value of these coefficients. The inverse PNN can help us to determine the exact value. The prediction coefficients are very close to the reference 0.1 that we set over here. Another scenario is just like what I said before. We have no idea what would the effective term that pair in our equation. So would it be the first derivative or the second derivative that we don't know. So inverse PIN will solve our problem. If the term is not effective, a very low value of coefficient would be given in the equation, as you say in this blue color. Thus, PNN is very powerful in the inverse discovering of the undetermined PDE in an unknowing problem. So PNN is very powerful in engineering and scientific problems related to the PDE solving. But more importantly, PNN really gives us a hint where we can incorporate the additional information into the NN in the form of constraint, and thereby to improve the overall NN's performance. To say, if you are trying to use the neural network to approximate some engineering or scientific process in your own problem, was there any physical laws or constant that can exist in the process that the whole process have to obey? So this kind of thinking might help you to improve your NN. So the fourth and the last topic today is in the regime of biophysics. So specifically, we are going to talk about the red blood cells or RBCs. So RBCs are most common cells involved in the blood circulations. The circles through the blood circulatory system during their normal lifespan of around 120 days, transporting oxygen from the lungs to other tissues or organs. So RBCs naturally has a shape of biconcave and highly deformed. And then they are highly deformable to pass through the narrow capillary channels. So the morphology of the RBC can be seen as a vital indicator of our blood health. So the basic logic is that if RBC displays an abnormal shape, so it's going to highly caused by some pathological factors, which can also influence the regular mechanical properties of RBC as well as their deformabilities. So RBC would become in this way, RBC will become harder to pass through the narrow blood vessels, thereby causing some blood disorders like SAA or malaria. So, except these horrible diseases, so the morphology change also occurs in the normal aging process of RBC. Therefore, scientists have been investigating this RBC morphology for many decades. So as computational methods and numerical simulation become popular, people are building different models to conduct a variety of simulation study the dynamic behavior of RBC in many scenarios. So this research are pointing out that I'm very accurate and well-configured RBC 3D geometry before the formal simulation is really important because it may determine whether the simulation is correct or not. So the conventional experimental methods to obtain RBC 3D geometry are reliable but of very high cost. So people are naturally think that the machine learning would like help to reduce the effort. So researchers, especially from the computer science, they have built up NN models that directly construct RBC geometry from the images. However, most of the models lack either the generalizations or efficiency. So we're thinking about will there be a smart way to do that? So let's just put the background of the RBC aside for a moment. Let's learn about a new NN framework, which is multi-fidelity neural network or MFNN. So MFNN deal with two kinds of data. One is high fidelity data that comes from a very accurate, detailed but expensive sources. In contrast, so the low fidelity data is cheap and easy to access, but usually less accurate. And these two kinds of data usually share sort of a connection or correlation. For example, we previously, like in topic 2 of the biomass, we combine both actual experiment data and the PPA simulation to train our DNO models. So the actual experiment data can consider as a high fidelity data, and the simulation data can be considered as a low fidelity data. Here we use a simple mass function example to show how MFNN works. So there are two sets of data. The blue dots are the high fidelity data points. They are very few. The blue line is a function that we want to approximate. So in contrast, the red dots are low fidelity data points. So there are many. The red line behind them is low fidelity functions. So though these two functions share some sort of a correlation. So if we use two separate NN to approximate two functions separately, the blue high fidelity one will naturally fail because the data point is too few. So the key idea of the MFNN is that we can use this kind of a correlation between two data sets, or to say the experience of how low fidelity data approximate to provide help for the approximation for a high fidelity data one. Thus, we can design our NN this way. So the network in the red box will learn the experiments to how to approximate the low fidelity function, and the networks in the blue box will learn the correlation between the two functions. Using MFNN, the high fidelity approximation result is pretty good. So we know the basic principle of how MFNN works, but how do we relate this kind of a MFNN to the RBC's 3D geometry reconstruction? So in our previous research that which investigates the relation between the RBC geometry and the biophysics, we have conducted a simulation where RBC deforms from a sphere to multiple stable shape by giving different physical property, just like the animation or the way I demonstrated here. So in the view of mass, at the input of the simulation, we have a list of coordinates forming the sphere shape. And at the output of the simulation, we have another list of corresponding coordinates from the stable RBC shapes. Thus, NN can be built to approximate this simulation process. So the thinking is, if we have one simulation that generates one RBC shapes, whether we can use this one as low fidelity case to help generate the other RBC shapes, which can be seen as a high fidelity cases. So relied on this idea, we build a MFNN using both sub-CNN and FNN to predict the variety of RBC shapes. In low fidelity CNN, we gave sufficient data points to approximate the low fidelity RBC reference shape to allow the low fidelity mapping can be fully approximated. Then we insert some partial, or to say insufficient data of the target RBC in high fidelity FNN. The partial data is sampled from the RBC cross-section because we want to mimic the reality of the experimental observation where only two images data are observed at a several fixed angle. So this is the validation result of the partial CNN parts. As you can see, with sufficient data points, the low fidelity reference RBC can be fully learned using the CNN. However, the approximation would fail if we directly use a single CNN with a partial cross-section data here. So then we have the full NN predictor. We test a variety of the RBC shapes. We found the dissimilarity between the low fidelity reference shape and the high fidelity target shape. So it means that two shapes should share sort of a geometrically similarity. So we use a reference shape in the same category as the target shape to reduce this sort of initial dissimilarity. So following this principle, MFNN prediction with at least two cross-sectional data gave prediction of the average accuracy around 95% using our simulation data. So in the real application scenario, we can use MFNN to create a 3D digital model directly from 2D images. As you can see, we try different kinds of RBC images where they present the different shapes. So our MFNN-based tool can do the same process, just like those conventional microscope. So MFNN really gave us another hint that we can utilize the correlation among the correlated data sets to refine our surrogate NN model. So to conclude our introduction to today's topic today, there are many takeaways. So the first thing I want to say is that the neural network is nothing but a universal approximator. It can map any functions or mappings. When we study an engineering or scientific process, always try to deduce a problem first into a very simple math language. Try to think about can our input and output of the study process can be described in a simple math functions? Is it possible to use a mapping to connect the two processes? Regarding our models that we introduced today, so the DNO model is a very powerful tool to approximate the function from one functions to another functions, and with considering the key external factors as well. So, and the PINN is powerful in solving PDEs and inversely discovering undetermined PDEs. And it gives us hint that we should always look for process constant to provide additional physical information for NN training. And for MFNN, just I mentioned, MFNN gave us a hint that we should use a correlation among the data to enhance our surrogate models. And that's all the topic content that I want to share today. And finally, I would like to, of course, thanks AIM for the composite AI Art Center and the inverse design training in advanced and sustainable composite NSR research program for giving me this opportunity to present this webinar. And also thank DOE for the funding and all the other collaborating university and institute. Thank you.